Hi, everyone. My talk today is Pounding Blockchain for Fun and Profit. Am I going to share a bug in Solana me and my friend found a while back? Here's a quick introduction of myself. I'm Ginoah, currently working as a red teamer. I also play CTF with Spelson, and sometimes do bug bounty with a few friends under the handle Anonymous in our free time. Unless you've been living in a cave for the last few years, there's no doubt you have heard of blockchain at some point, likely along with all kinds of description, stuff like Bitcoin to the moon, NFTs, future of finance, and all kinds of other snake oil. But none of those really explain what a blockchain is. So here's a quick introduction of blockchain. At the very core, blockchain is essentially a distributed database. The difference is that it is designed to require minimal trust between each node running the software, or more often referred to as validators. I won't go into the detail of how this minimal trust setup is achieved, since it is quite complex and beyond today's topic. But it boils down to some consensus algorithm that detect misbehaving validator and penalize them. The target we're looking at today, Solana, is one of those modern blockchains. It is written in Rust, uses a variance of BFT algorithm with proof of stake for consensus, and includes a VM that runs a custom modified fork of eBPF, which is called RBPF. We can understand RBPF simply as a VM runtime for smart contract, or what we call program, which is written in Rust also. And before we get started, the bug presented today is introduced in an optimization-related feature in release 1.16. We reported it approximately a year ago, and the bug has since been patched. Here's the index of today. We'll begin by discussing some basic concept of Solana, then we dive into the legacy model, how validator load account data from the database, execute a program, and then commit the result back to the database. After that, we'll explore what direct mapping is and why it's important. We'll also look at how the new model changes after direct mapping is introduced. Finally, we'll talk about the bug and the exploits. Now, let's begin with some basic concepts. As mentioned earlier, blockchain are basically just databases. So it is easy to see that keeping track of some persistent data or state into its state is the main purpose. In Solana, the data are stored in key value pairs, where the key is some 32-byte identifier, which we usually call address. And the value is a data structure called account. Account includes several fields, such as LAN port, which is just a fancy name for the Solana token balance of an account. Other fields like data, which holds general-purpose data created by Solana program, is also tracked by the account. And the other crucial part is transaction. Everything we want to do on a blockchain happens through transaction. Now, there are two key components of a transaction, instruction and accounts. Instructions are basically individual calls to a program. This could be a system program or a smart contract written by a user. A single transaction can include multiple instructions, and it's atomic, which means if any instruction fails, the entire transaction is rolled back. Then we have accounts. In a transaction, we have to specify all the accounts that might be accessed during the execution of all the instructions. These accounts are split into two sets, a read set and a write set. This marks them as read-only or writable, allowing Solana to execute non-conflicting transactions in parallel. So let's dive into the background of how Solana managed data storage during transaction processing. Let's start with looking at the original 1.14 internals, which we will refer to as legacy mechanism from now on. This is how the VM accesses its data. The RBPF runtime memory layout is straightforward, with 4 sections, similar to other common process layout. There are codes, stack, heap, and an input section where data loaded from the database is stored. Each section is assigned a fixed size and a virtual address. Here's a view of how accounts are loaded into virtual memory. At the beginning of every transaction, the account list mentioned earlier is loaded from the database and stored in an account shared data structure within the transaction context. Later, these accounts are serialized into the input region, allowing the VM to access them. For example, account 0 and account 1 are serialized into the input section, with all fields such as the key, owner, LAN port, and data being serialized together. If the instruction includes the same account more than once, for example, account 0 is include toys, and account 2 is created as a reference to account 0. After loading the account into the memory, account info structure are reconstructed from the serialized data. This is done to make life easier for the contract developer to interact with the account passed into the VM. An entry point routine within the RBPA program constructs an account info structure used by Solana programs, and these account info structure are stored on the heap. Key attributes like owner, LAN port, and data in account info reference back to the corresponding memory in the input section, so any changes made in the account info are directly reflected. During the runtime, the RBPA program has full control over its virtual memory space, so user can manipulate memory within the VM however they want. Recall that accounts are loaded into the input section, regardless of whether the account is owned by the program or not. So we need to implement some sort of permission check to prevent someone from modifying the LAN port of other account. Since all the data inside the VM is temporary, the main thing we care about is the account's write permission when committing the execution result back to the database. There are a few rules that must be followed. For example, the account must be marked as writable in the instruction if the program wants to modify its content. Only the account owner can modify its account data or decrease the LAN ports. And the total sum of LAN ports has to remain consistent. For simplicity, let's say that only the account owner has the permission to write to that account. At the end of the execution, the data in the input region is deserialized and written back into the per transaction account cache, which is transaction context. This is where all the checks are applied. All the validation rules we mentioned earlier must be satisfied before writing back into transaction context. After execution, if the entire transaction succeeds, the content within the transaction context are committed back into the database. The data is persisted, the transaction ends, and then it moves on to the consensus process. And that's it. Deploying a contract and calling it from an external owned account is simple. But what if we want to implement a more complex system that requires interaction between multiple contracts? We need a more sophisticated mechanism to pass data between VMs. This is where the CPI, cross-program invocation system call, comes into play. First, let's take an overview of the legacy interrupt process. When one program tries to invoke another, it crafts an instruction and calls the CPI syscall. The instruction is analogous to instruction in a transaction and specifies which program to call as well as all the account involved. It first fetches the account metadata specified by the instruction to learn which account are used, as well as whether they are variable or whether they are signers. Next, using the public key, it looks up the corresponding account share data in the transaction context. This allows us to write the validated change back into the transaction context later, which serves as a per transaction cache. The third step is to retrieve the account info corresponding to the public key and translate the virtual address, such as LAN port and data, into host pointers. These pointers are stored in a structure called caller account, so they can be used later easily. Finally, we have the account info we needed and account share data as a cache. We then go through the validation rules mentioned earlier. Once validation is complete, the data is written back to account share data. And later, when actually executing the invoked program, the next program will serialize this account into its input section, just like we talked about before. At the CPI boundary, all changes to account must be validated to ensure they are legal before passing them to the next program. Otherwise, we risk allowing illegal updates. Since Solana program does not allow graceful handling of failure in the CPI caller program, the VM can safely assume that if the callee fails, the entire transaction will be reverted. This allows the VM to treat the CPI boundary as a checkpoint and flush all the validated change into the per transaction cache. This design allows the VM to reuse the account cache while serializing data into the CPI VM memory. Leaving the CPI scope is similar to finishing execution, except changes to account data must be written back into the parent program's VM memory to reflect their updates. Just like when exiting an outermost instruction, we retrieve the account from the VM memory, go through the validation rules again, and then write them back to account share data. Before writing the data back to the parent program, we check if the original VM has preserved enough space for potential data growth. The amount of preserved memory is controlled by a constant, which limits the account data growth per transaction. If the child VM attempts to grow data beyond this limit, the transaction reverts. When the check is done, we can simply copy the data and other properties back from account share data into the parent program's memory. So it works, but the current serialization and deserialization-based account passing scheme require copy when entering a new context and another when leaving it. These data copies are costly and create a bottleneck for execution speed. To address this, an optimization called direct mapping was introduced in version 1.16. The overhead only becomes significant when the length of data being copied is large, so we only need to avoid copying data field. Also, copy is not necessary when reading account data. It is only required to prevent data pollution when writing it to an account. With a new direct mapping mechanism, this is how the new data exposure looks like. Instead of copying the entire buffer, it directly maps the data vector buffer into VM memory. We can think of the legacy input section as a single block that is allocated all at once. The new data exposure breaks the input section into multiple parts, with some portion residing inside memory specifically allocated for the VM, while account data directly mapped to the actual data vector owned by account share data. Due to the direct mapping of account data, VM writes to those memories are now editing account cache data directly. Thus, every single write to the map region must be validated. Failure to do so could allow illegal writes to succeed. The view of account infrastructure for Solana programs remain unchanged. The key LAN port and owners still point to the serialized data in the input section. However, the data field now points to the directly mapped section. When data is written, the VM now resolves the corresponding virtual address to a host share memory instead of a memory dedicated for the VM. Now, we have the basic understanding of how the new data exposure is. Let's cover two concepts we skipped earlier: how copy on write is achieved and how the VM manage its memory. Remember the data in account share data, which is a reference of vector. It is actually point to the same data buffer as another account share data instance in the account database cache. The data is only copied when the write occurs. Once the data write occurs, a new copy is created. However, the legacy implementation doesn't guarantee that the data will only be copied once. Recall that the reserved data buffer within the serialized account, the serialized content in the input region. This buffer is reserved to handle potential growth in the account data length. Whenever we increase the data size upon entering or leaving a CPI, whenever the account share data buffer is not large enough to hold data that should be written to it, we need to relocate the account data buffer, resulting in an additional copy. Every time we relocate a new data buffer, we have to copy the old data into the new buffer. Note that only the data reference in the transaction context is updated, while the data reference in the account DB cache is only updated when committing the transaction. The new data exposure mechanism aims to eliminate this excessive relocation by reserving a maximum bytes of spare memory during the very first copy on write. This ensures that in the majority of cases, at most one relocation is needed for the entire transaction. The second concept we'll explore is how VM memory is managed. Earlier, we thought of VM memory as an isolated space and only occasionally mentioned translating VM address to host pointers. Now, let's see how these addresses are translated. There's a structure called memory region that records the mapping between host pointer and guest address, along with fields like data length and an isWritable flag. Every time the VM tries to access the virtual address, it locates the correct memory region, translates the guest address to a host pointer, and then finally access it. In the legacy model, memory regions have their own dedicated buffer, with each section, such as input, having its own memory region mapped to a single large buffer. This memory region remains unchanged throughout their entire lifetime. However, in the new model, the data buffer is directly mapped into VM memory. but the other fields are not. To be more specific, when the VM tries to read or write account data, the address is mapped differently. Instead of pointing to the input section's buffer, as in the legacy model, it now points directly to a data buffer on the host heap. This buffer is shared with other structure. The other fields remain unchanged. When accessing field like LAN ports, it's still resolved to a dedicated buffer, just like in the legacy model. This requires us to split the input section into multiple memory regions. It's worth noting that the memory region structure has also been slightly modified. We will talk about that later. Another thing worth noting is that the host address in the new memory region may change due to data relocation. Recall that we need to relocate the new data buffer when the data grows. This is the old buffer. When the new buffer is allocated, both the pointer in account shared data and the host address in the memory region must be updated. But all other fields except for state remain consistent throughout its lifetime. This means the reserved data buffer doesn't benefit from direct mapping. When trying to write into the growth area, the guest address actually still point to the reserved data buffer, not account zero's data, which is a mapped. Therefore, it still requires an additional copy to the actual data buffer during account writes. Now, let's talk about the state field in the memory region. There's a state field in the new memory region structure that we haven't discussed yet. This field is crucial for permission check on the data writes. So let's see how it works. The readable and writable state correspond to the isWritable flag in the legacy memory region. Previously, the entire input section was marked as writable, as it contained both account that the program had write permission for and account it didn't. This meant we had to perform data write checks retrospectively when exiting the VM. Now, with direct mapping for account data, we need to apply check immediately as the write occurs. This is done by assigning the correct readable and writable flag to the memory region, overseeing the data buffer. The copy on write flag is used to handle the buffer reservation we mentioned earlier and serve no other purpose. Once a copy occurs, it changes to writable, so we can ignore it from this point onward. To summarize, we only need to focus on the permission of memory region that are directly mapped, as all the other fields will be validated when writing back to account share data. Managing memory region access using state means we need to know the permission upfront. Fortunately, the rules are consistent within a single VM context. For example, only the account owner can modify data, and account fields are writable only if the account is marked as writable in the instruction. Now that we know which permission to assign to memory region during creation, let's see what happens when we try to commit the account. The process is quite similar to before, except for updating the data buffer. For other fields, such as LAN ports, we simply validated them and write them back into account share data. For the directly mapped data buffer, the section from the start up to the original length has already been modified through direct mapping. However, if a write has occurred and the data length has increased, we still need to update the data beyond the original length and update the data length. As that part is still in the reserved data buffer, we have to perform an additional copy. With data writes handled, the next thing to understand is how CPI works in the new design. The CPI code is quite similar to the original design, but we don't need to copy the entire account data anymore since it is now directly mapped. Most of the process remain unchanged. First, we retrieve the metadata of the account involved in the CPI instruction. And then we look up the corresponding account share data from the transaction context. Then we translate the guest address in account info into a host pointer to construct a caller account. And here's where things differ. Instead of copying the entire account data, we only have to copy the newly grown data that is still in the reserved data buffer back into the newly allocated direct map buffer. Finally, we validate other account changes and write them back to account share data for further serialization. The major difference occurs when returning from a CPI calls. Since we're using direct mapping and a vector copy on write might occur during nested calls, we need to check if the original data buffer mapping has been relocated. If the data buffer has been relocated, we need to update the original mapping in the parent's program's memory region to reflect this change. Just like when entering a CPI call, when returning from CPI, we need to copy the data from the reserved buffer back to the directly mapped data buffer, validate all other changes, and then write them back to account share data. Second, we check if the data buffer has been relocated. If it has, we need to replace the parent's data mapping to reflect the change. The rest following the same process as in the legacy model. We perform some checks and update the account changes back to the parent program. So, how exactly do we perform relocation check and update data mapping in memory regions? Remember, mapping are managed through memory regions, each containing a non-overlapping range of virtual address. We also have a VM data address that stores the virtual address of the data in the parent VM. The solution is straightforward. We look up the memory region corresponding for the given VM data address, where VM data address should match the VM address in the memory region. Then we have the memory region mapping the data buffer, which is still pointing to the old data buffer. Next, we check if the host address match the current address of the account data buffer. If they don't match, this means the relocation has occurred. So we update host address in the memory region to the current address of the account data buffer. After updating host address, the memory region now correctly points to the new allocated buffer. Finally, now we have covered all the background mechanism we need to understand. So finally, here's the bug. When returning from CPIs, in the replacement procedure, update caller account is called. We search for memory region the memory region with VM data address in the caller account, and then update the host address if host address in the memory region doesn't match the address from account share data. Here, two questions arise. How does a CPI know which region to update? And where does that virtual address came from? We search through the list of memory region for a matching virtual address, but the virtual address we compared against came from caller account, which is constructed using information of account info from the VM heap, which means it is fully controlled by the user. Nothing ensures that virtual address points to the correct data of the account. Here's the data process. Here's the detailed process how we trigger this bug. Let's revisit the new CPI call process. In this attack scenario, we assume we have two accounts. Account 0, which is owned by our program and is writable, and account 1, which is not owned by our program and is not writable. And we want to gain access to the account 1. Since a program data is stored in its data buffer, if we can modify another program's data, we can arbitrarily change its state. In most cases, this will allow us to steal funds or NFTs from that program. Since heap memory is fully controlled by the user, let's say we modify the pointer of account 1 in the ref cell, where account 1 is now owned by our program, where account 1 is not owned by our program, to point to the data of account 0, which is owned by our program. Then the CPI call starts. First, we collect the metadata of the account involved in the instruction, and in this case, we make only account 1 included in the CPI call. Then we translated the account info of account 1 to construct a caller account. As we modified earlier, the data address of account 1 in account info now is actually points to account 0's data buffer. As a result, the VM data address in the caller account will also point to account 0's data buffer. But remember, we still need to pass the check for this CPI call to succeed. The right check on account share data must not fail. This will hold true if either account 1's data is the same as account 0's data at the time of CPI call, or account 1 is writable by the caller program. Since data address of account 1 is now pointing to the data buffer of account 0, so we'll be fine. Upon returning from the CPI, we'll go through the data buffer replacement procedure. When returning from the CPI call, the caller VM memory looks like this. The lookup process tries to fetch the memory region for account 1 data, but since account 1's data now points to the account 0's data address, the memory region for account 0 data will be fetched instead. Currently, the pointer in memory region is still pointing to the original account 0's data buffer, and the replacement procedure starts. The code checks if the host address in the memory region matches the account 1's data host address. Since they don't match, the host address in the memory region will be updated. As a result, the memory region of account 0's data will now point to the buffer of account 1's data. And because the memory region for account 0 is writable, we can now freely modify account 1's data using it. But sadly, that doesn't work. Here's what happens. The account 0's memory region host pointer is modified to point to account 1's data buffer. Recall that account 0 is owned by the program, but account 1 is not. So account 0 data memory region is writable, and account 1 data memory region is read-only. So can we just use account 0's data pointer to modify account 1's data buffer now? No, we missed something. When returning from the CPI, the memory region will be updated. The writable state of account 0 will be changed to read-only, as the VM will think that it is updating the memory region of account 1. So the attack will fail. So here's the new plan. Instead of targeting an account we can't write to, let's target 2 writable accounts of different lengths, account 0 and account 1. They are still mapped with memory region 1 and 3. The key difference is, this time is that we have write permission for both accounts, and the data length of the account 0 is longer than account 1. After the replacement procedure, the host address in the memory region 1 will point to account 1's data buffer. This allows us to use account 0's data pointer to access account 1's data. Since both accounts are owned by our program, there are no permission issue. But notice that the account 0's data length is longer, so when accessing the later part of account 0's data, it will go beyond account 1's data buffer. This gives us out-of-bound access to the host memory. The Rust heap contains many data pointers, so turning this out-of-bound into arbitrary rewrite and ultimately remote code execution is also possible. Here's the detailed step to gain arbitrary memory rewrite primitive. First, we need to prepare 3 accounts owned by the attacker program. Here's the initial state. We omit memory region irrelevant for the exploit and only show memory region 1, 3, and 5, which corresponds to account's data buffer that we'll be using. Similarly, we only show account share data for account 1, since it is the only account that will be passed through CPI to trigger our exploit. Notice that the data buffer for account 0 is larger than those for the others. We will leverage this size difference for out-of-bound memory access. The first step is to modify account 1's account info data. Modify account 1's account info data pointer in the ref cell to point to the data buffer of account 0. Then initiate a CPI call that includes only account 1. This will construct a caller account for account 1, but its VM data address will point to the data buffer of account 0. In the calling program, we return without doing anything. When CPI returns, it initiates the replacement procedure, checking if the data buffer of the caller account has been relocated. It tries to retrieve the memory region using the VM data address in the caller account for account 1. But instead of finding the memory region of account 1, it finds the memory region of account 0, believing it is the memory region of account 1. Next, it compares the host address in memory region 1 with the data pointer in account share data 1. Since account share data 1's data pointer currently correctly points to account 1's data buffer, which is different from the host address, it assumes the data buffer has been relocated. It then updates the host address in memory region 1 with the data buffer of account 1. This causes memory region 1 to point to the incorrect data buffer. And since account 0's data buffer is longer than account 1's, this gives us an out-of-bound memory access. Next, we attempt to scan and egg hunt memory region 5 on the host heap. We can simply revert this transaction and try again until we successfully find memory region 5. Once we found the memory region 5, we override its host address to point to wherever we want, giving us read and write access to arbitrary address. For example, let's say the return address on the stack is located at 0x.beef. We simply override the host address of memory region 5 to 0x.beef. Then write to it through account 2's data buffer. This allows us to hijack the program counter when returning from program execution. From there, we build a ROP chain to gain remote code execution. Here's the demo. On the right, we have 2 windows for the attacker with IP 0.2. On the left, we have the validator running with IP 0.3. First, we start the validator with version 1.16 and all default configuration. We also have uncat. Listening on the port 10101, waiting for a reverse shell. The exploit script deploys our attack contract, airdrops the necessary funds to the involved accounts so they can pay for the data storage, and then finally trigger the exploit. Let's wait a sec for the validator to handle the transaction. As we can see, the reverse shell connects back from the validator, and we can, for example, get the validator node's private key. Yep. And that's pretty much all I have to show for today. But before ending the talk, let me share some of my thoughts on the state of blockchain security. First and foremost, blockchain security isn't just about dumb smart contract bugs. As we have seen today, the infrastructure behind blockchain is incredibly complex, with the software constantly evolving and under development. When there is complexity, there will be bugs, and sometimes even interesting bugs that are just as sophisticated as those we've seen in other well-established targets. I know a lot of security people who dislike blockchain due to the culture around it, but honestly, just give it a try and you'll see it could be quite an intriguing and lucrative target. Secondly, it's also worth mentioning that this is a prime example why low-level exploitation wouldn't die even if people switch to so-called secure language. There's always need for optimization or low-level programming when using unsafe code. As long as people resorted to unsafe code, there will be bugs. Finally, what I have touched today is arguably the simplest part of blockchain. While blockchain are kinda a product without a demand, it actually pushing the frontier of several fields, ranging from consensus algorithm to zero-knowledge proof. There's an entire range of topics to be explored. And new technology often comes with new security issues. Hence, I'd love to invite people to hop onto the party and join us in breaking blockchains. Thanks for listening.